Okay, so let's look through what we want to do for the audio processing lab for signal processing. What I want to point out is that the directions are pretty self-explanatory, but I want to make sure that I highlight things that are very important. For example, reading the audio file in. The key here is that we're going to use the audio read command, and the syntax for that is that I'm going to take a vector, which is a square bracket, which is going to be x comma fs, where x is the actual data and fs is the frequency of sampling, the sampling frequency, and then it's going to be equals audio read, and then whatever file I need, in this case the hello.wave, needs to be represented in single quotes. All right. Next thing we want to do is transpose the vector x so that it's in the right direction. And then we can define a vector for the number of delays. So how many times I want this to repeat. All right, more accurately, this is the number of repeats. All right, then I need to check the length of my delay. All right, that you can vary. That really depends on what you're looking for. Then we want to pre-allocate a vector for calculations and put the original signal into that vector. And then we're going to use a for loop to compute the end signal. All right, so there are some cute little tricks here. We're going to go from k is equal 1 by 1 to the length of nx minus the length of delay, meaning that we need to create a y that actually has addressable vectors, which is means we need to get rid of the length of delay at the end. And then to be able to hear the output file, we want to use audio write, and we do that using hello no decay dot wave comma y comma fs. So we want to choose the file name, choose the output, and then choose the sampling frequency. All right, and then the next thing we want to do is define some exponential decay. In this case, I chose a equal to 0.1. You can play with that and decide what you like or don't like. And essentially, we're just going to create that exponential decay and multiply it by the y value, and you can kind of see that from that. All right, the other part is doing a Hall reverberation algorithm, and let me first open, as I'm talking, the Simulink Model file, and as that's opening, what I want to say is we define fs for the audio signal. In this case, the audio signal that I'm giving you has a sampling frequency of 44,100 hertz. Okay, so let's look at the actual Simulink model. You'll see that I have a couple of subsystems. I've got the input, which knows that it's called input and the sample time is 1 over fs. I've got the output, which is an output with a variable named y, and it inherits its sample time. Okay, and in fact, we'll be very careful. It's saving as an array. That's really important that it does that. All right, we have some early reflections here. This is a set of sorry, I zoomed out. This is a set of delays. Each delay has a length delay, which we set in our M file. And then we have the late reverb generator, which is a set of all-pass coloring filters with a low-pass filter and some late delays. These are all parameters that we can play with, but what I will point out is that it's not that important for now. So I set fs, I set the reverb parameters, delay, late delay, decay. All right, these are things that you can play with and see what you get. And then you read in the sound clip. We have time, we have input. Be very careful to make time transpose. That's what this single quote there does. It needs to be the same size as x. All right, and then we're going to run the Simulink file using the sim command. And we'll just sim Hall reverb. We'll get the output y. We need y to be smaller, so we're going to compress it by divided by 200, make it smaller. And then we're going to take an audio write, and what it will do is save the file that we have, so that way we can listen to it and hear the difference. All right. Of course, I will play these things in class so that way you get a feel for what you should get.